I'm Shub. I lead solutions engineering here at Arcade. To start off, we're going to go on a deep technical journey. Our goal is to trace a single prompt, which is summarize last week's PRs and file a bug from the moment it's typed in a browser all the way to the GPU fabric that's executing the inference. And this isn't just going to be a high-level architecture overview. We're going to get into the weeds. Like we're going to talk about package structures, memory layouts, scheduling algorithms, and protocol wire formats. So why should you care? Because of three things, right? These three things consistently break AI applications in production before model quality ever becomes an issue. The first problem is frozen token streams, right? You're demoing, you can think you're demoing an AI assistant to your stakeholders, and they might be on bad Wi-Fi. They can be on a hotel's Wi-Fi with 2% packet loss and 150 milliseconds RTT. The tokens start flowing, but then they suddenly freeze, and then 5 seconds pass, and then you get bursts of 20 tokens all at once, and then another freeze. And your demo looks broken, but it's not the model. It's actually the TCP head of line that's blocking at the transport layer. The second problem you get into is the identity crisis. So your agent successfully files a GitHub issue, but it's attributed to a service bot instead of the actual user who made that request. Now your audit trail is broken, right? Your compliance team is going to be unhappy, and you can't trace which human authorized which action. And the third problem is vendor lock-in. You spent 3 months integrating with model server A, but now you want to try model server B for better performance, but you'd have to rewrite all of your client code because APIs are incompatible. And now your agile AI infrastructure is actually brittle. So today's mission is going to be to fix all three problems by making deliberate protocol choices at each hop of our prompts journey. So we'll cover 5 major decision points and demystify 2 concepts that engineers often hand wave. First is what NVIDIA Triton actually is, and the second, if we have enough time to get to it, I want to talk a little bit about key value caching, which dominates your GPU memory budget. By the end, you'll have a mental model you can apply, hopefully, in your actual work, and all with measurable metrics and some implementation steps I'll go through. So to begin, let's look at the architecture at 1,000 feet, right? So let's establish the complete map. So our prompt will traverse these 3 distinct planes, right? The first is the tool plane. This is where the Arcade MCP is. This is where your tool calls sit. It's where you handle identities for AI agents that are actually taking action. It's where policies and your audit logging lives. And most importantly, this does not touch your inference requests. And this is where it fits into the architecture. Second is your inference plane. So this is completely separate. The orchestrator speaks kserve v2, and we'll get into kserve v2 later on. And through kserve v2 directly to model servers like Triton, there is no gateway, no identity injection, just standardized inference protocol. The third is your agent orchestrator. We'll look into HTTP3 and HTTP3 web transport specifically for the last hop to eliminate TCP head of line blocking and ensure smooth token streaming even on lossy network. Now, this separation matters because mixing tool calling, right, with MCP and things like that, and AI agentic frameworks with inference creates a single point of failure. This might complicate your security audits and make it impossible to swap model servers without touching your authentication logic. So let's start with stage 0. Before the prompt ever gets to the inference, right? The problem is sending everything upstream. So traditionally, the browser captures the user's prompt and immediately sends that raw text to the server. This has several issues. First is privacy. You've got sensitive PII like emails, phone numbers, account IDs that are leaving the device unprotected. There are bandwidth issues where large prompts can consume precious last mile bandwidth. And of course, time to first token, because the server has to do all the work, including all of the pre-processing, time to first token also goes up. The solution to this is our first protocol choice, is we can run small, efficient models in the browser using these two emerging standards. WebNN, which is the Web Neural Network API. It provides a standardized JavaScript API for machine learning that targets device-specific machine learning accelerators, and it's going to help developers to access hardware capabilities like NPUs and GPUs and things like that. And then the second is on ONNX runtime web with WebGPU. So getting into start with WebNN, as I was saying, it'll enable developers to access hardware capabilities like NPUs, GPUs, and specialized machine learning processors through a unified interface without worrying about vendor-specific implementation. It provides that unified API for neural network graph compilation. It gives you access to platform-specific acceleration. So if you're using Apple's Neural Engine, Intel NPU, Qualcomm, and it's model format agnostic. So it can work with ONNX, it can work with TensorFlow Lite, and so on. Now, ONNX provides, and ONNX's runtime web provides production-ready web GPU execution capabilities, which will allow you to run neural network inference directly in the browser with GPU acceleration. And I've provided some of the stats here directly, but what we get with using these two together is like you can ensure that PII never leaves a device in plain text. Metadata map is encrypted with the orchestrator's public key, and the server can rehydrate PII only when necessary. And the implementation complexity of this is very low. You can load up a pre-trained ONNX model, which is about 5 megabytes. It's about 200 lines of JavaScript code, and it degrades gracefully, so it can fall back to server side if WebNN is unavailable. Now that we've got that stage 0 done, let's move on to stage 1. So this is our first hop in the transport. Now, as I get into this, I want to start by taking a look at how we got to HTTP 3 today and the evolution of HTTP and why it really matters for AI. So let's understand like why we're making a protocol choice here by examining the history a little bit. Now, with HTTP 1.1, this was introduced around 1997. It's very sequential, right? So the problem here is you get one request at a time per connection. Now for AI, this would mean you can't interweave like a prompt upload with token download, and each tool call will block other tool calls. And the workaround of multiple connections is just a resource waste. And we saw this not only with AI, but just with traditional websites. So in 2015, we got HTTP 2, which is multiplexing on TCP. HTTP 2 introduced multiplexing of multiple requests over a single TCP connection through a framing layer. But this created a new problem because TCP itself doesn't understand these individual streams. This is TCP head-of-line blocking. So when a packet is lost, all subsequent packets must wait for its retransmission, even if they contain data for unrelated streams. And for AI token streaming here, this is you get token rendering freezes for 1 to 3 seconds, burst of 10 to 20 tokens suddenly. Users can perceive this as like stuttering or broken. And it happens most when you're on mobile networks, hotels and cafes, international connections, or you're using a satellite. So this is the first problem that we're tackling. And you can think about this. You can measure this impact about like a 3% packet loss, and HTTP2's throughput can degrade by 30 to 40% compared to its theoretical maximum due to this head-of-line blocking. So with that, in 2022, we got HTTP3 and Quick. And Quick is essentially TCP 2.0 running over UDP. It's providing independent streams where loss on one stream doesn't block others, while maintaining all of TCP's reliability features like ordering and congestion control and flow control. So with that, let's take a look at our second protocol choice, web transport. This is going to be the API layer. Now, web transport provides applications with nearly direct access to Qwik's features through unidirectional streams, bidirectional streams, and unreliable datagrams, which can all be multiplexed within the same HTTP3 connection. So for unidirectional, you can go server to client. Bidirectional, you can have request and response pairs. And for datagrams, you can have unreliable, out of order. And this is perfect for hints, right? Now, with HTTP3, with Qwik demonstrates significant better performance on lossy networks, with packet loss in one stream not affecting the other stream's progress. So with an implementation of this, you can upgrade only the browser to the gateway hop. You can keep gRPC and HTTP2 internally because they're well matured and you've got that already well tooled. And you can also measure inter-token P95 latency and time to first token. Now, let's move on to stage 2. This is the identity and the policy layer. Now, the core problem here is that agents, and AI agents specifically, need to use tools, right? It needs to read a file from your Google Drive or create a GitHub issue or send a Slack message. But it needs an identity to do that with, right? So the question here is, under whose authority should it act? And with OAuth, we created OAuth and OAuth 1 and OAuth 2.0 and OAuth 2.1, we created this idea of delegated authorization. And as we were building out MCP and tool calling and all these things, we had a lot of bad answers to under whose authority should it act. And the bad answers was, the couple of bad answers we had was, what if we just use service accounts, right? And give the MCP server and the tools access to a super admin credential. But this breaks audit trails. You can't attribute actions, and then the server, the tool server itself becomes a risk. We tried passing user tokens directly to the agent. Now, that's massive security sprawl. You have no policy enforcement, and again, it opens up your user tokens to be able to be used by an LLM without you choosing to do that. How about if an agent manages its own auth? Again, same security problems, but you also can't revoke access, and there's no central audit. Now, a good answer to this that we as an industry decided as we're building up MCP is to create a centralized gateway with per user, per method token injection and policy enforcement. Now, with this, we've got 2 protocols and 2 concerns to think about. So I've talked about MCP, but we also have to think about A to A, so agent to agent. This part of it shows which agent acts and when. And A to A is Google's protocol that handles capability discovery, task lifecycle through agent cards, define which agents can perform which tasks and actions and how they're delegated between agents. Now, MCP, on the other hand, is Anthropic's model context protocol, which provides a standardized way to expose tools and data sources and prompts through MCP servers that applications can mount with user context. Now, I work at Arcade, so I have to talk a little bit about Arcade. This is where Arcade's value really comes in, right? So Arcade provides a multi-tenant MCP gateway that solves identity and policy. So here's how Arcade works. At runtime for the MCP tools, Arcade injects a user token, and Arcade, because it is outside of the agent loop itself, and it is also outside of the MCP server and the inference plane, is able to intercept the requests that the LLM is making. It's able to apply policy. It's able to check for user credentials. And then once it is verified that the user is authorized to do take such an action, it will take care of calling that tool and injecting during runtime the user token so that the tool can be invoked. Now that we've got tooling and understanding how agents fall into this, we can go on to stage 3. Now, this is the inference plane. Again, this is separate from your tool plane and your agent plane. So in the inference plane, one of the problems we have here is vendor lock-in, right? Imagine you start with, oh, I feel like I'm missing a couple of slides here. But imagine you start with TensorFlow serving one of your models, and then you want to switch to Triton for better performance. You would have to rewrite every client, and your portable inference becomes like actually fragile. What Kserve v2 provides is a standardized interface for model inference across different frameworks and serving systems, and it provides a health, metadata, and inference APIs that work over both HTTP and gRPC. And the health API provides liveness, readiness, model readiness, metadata. You can get server info and model info, and of course, the inference API is your actual model call. Now, this Kserve v2 defines the envelope. Then this is the request and response structure, but the streaming transport is implementation specific. So if you're choosing to use a Triton server or a Torch server, you might do HTTP streaming using chunk transfer encoding or SSE, depending on your choice there. But the key point is the message format stays exactly the same. It uses v2 JSON, and only the transport framing changes. So Kserve v2 is a protocol that is endorsed and implemented by some major inference servers, including NVIDIA Triton and TensorFlow Serving and AMD Inference Server. Now, I want to deep dive a little bit into NVIDIA Triton itself. And here's what engineers can get wrong about Triton. Most people think that Triton is just another model server like Torch Serve, which is wrong. Triton is a scheduling and optimization layer that sits between the network and your backend frameworks, with a stable Kserve v2 API on one side and a pluggable execution backends on the other. Now, the way that this works, Triton's architecture has 4 layers. You've got your config file, which controls all of your scheduling and execution. You've got things like dynamic batching, shared memory extension. We can talk about zero copy as well, and then concurrent model execution. Now, the config file, this is just a quick overview of what it looks like. It controls everything about how Triton schedules and executes your model. And this is a very easy definition here, right? But you can imagine how this can get even deeper and deeper as you decide to use multiple different plugins with Triton. Dynamic batching is also another thing that you can use with Triton, but the dynamic batching in Triton allows the inference server to combine multiple inference requests that arrive within a small time window into larger batches, which improve throughput for models that can process multiple requests simultaneously. Now, you do have some trade-offs here, like you've got to think about latency. So you can think about adding about 5 milliseconds for max queue delay for each request. For throughput, you can see about 2 to 3 times improvement and fewer GPU kernel launches. And it's best for high QPS scenarios where batching amortizes costs. Now let's talk about shared memory extensions. We can talk about zero copy, which is like the fast path as well. And the problem here is sending large tensors over HTTP or gRPC is expensive. And Triton's shared memory extension allows clients to communicate input and output tensors through system or CUDA shared memory instead of sending data over gRPC or REST, which provides a significant performance improvement by eliminating costly data copies. Now, you can get this in 2 flavors, right? You can get this on CPU and the GPU side. With system shared memory, it uses a temporary file store, and it's accessible to any process on the host. And this is good for pre/post processing with co-located Triton servers, and then CUDA, which is GPU shared memory, which is accessible to all processes on the same GPU. which is good for multi-stage GPU pipelines if you're doing, for example, tokenizer to model and then a detokenizer after that. Now, you may need to use this. In many cases, you might not need to use this, but if you have co-located pre and post processing or multi-model pipelines on the same GPU or high frequency large tensor workflows, definitely use shared memory. If you don't have that and you're doing things like distributed inference or low frequency inference or have untrusted clients, you definitely should not use this. Now, I was going to spend some time here going over KV cache as well. But before I do that, I want to talk about concurrent model execution. So with Triton's instance group configuration, it will allow you to run multiple model instances concurrently to use multiple GPUs or cores and overlap compute with data transfer, which improves overall throughput. And this really matters because with parallel execution, you can get 4 times the throughput if the model is small enough. You can do load balancing, so you can have Triton round robin across different instances, and there's also fault tolerance. So if one instant crashes, others continue. So I was saying I was going to talk about KV cache here a little bit, but that's going to go a little too far into the weeds. So to bring it all back, let's put it all together with what the decisions that we've made and how we've come to this. So we were able to go from the browser, do PI redaction directly on the device itself, go from orchestrator, find the correct agent, find the issue agent, use the correct user's identity and authorization to call, work with an MCP gateway to call the correct GitHub MCP tools. We're using Kser v2 and Triton to basically make sure that we're doing dynamic batches and we're actually able to do inference quickly so that we're not running into those problems of buffering or vendor lock-in. And we're able to complete that task and report back to the user very, very well. With that, I'm going to pause there. Thank you, folks. Are there any questions?
So my question to you would be, how do you approach the balance between giving AI agents enough autonomy to be useful while maintaining appropriate controls and guardrails?
Yeah, so in regards to like the presentation I gave, there's a lot of different places where you can add those guardrails. I spoke specifically about when an AI agent is using a tool. So we built all these primitives of OAuth where, for example, you have to delegate your identity and your access. It's the same approach we're taking today with AI agents, where we're saying, hey, I'm going to allow this delegate, this AI agent of mine, to be able to take these specific actions. Now, if you look deeper into it as well, you can also add additional policies on how inference happens itself. So, and how we're doing PII redaction and things like that. But this is a growing question that I ask every day as well. Like, which layer should we tackle specific AI agent policies in?
Got it. Thanks for sharing. So other question I would have is, and this is regarding like folks who are just getting started while building agents in production. I'm pretty sure like folks are in the early stages of the process. So what do you think would be the biggest challenge they would face, or what would be your recommendation to them who are just getting started? Key thing they have to keep in mind to get these agents up and running as soon as possible.
Yeah, all an AI agent is a really good prompt and access to tools. I'm sure some folks here saw the OpenAI Dev Day presentation with Agent Kit, but if you look at the boxes that Agent Kit allows you to do, when you define an agent, you give it a prompt and you give it access to tools. And I think what folks will run into as they're trying to take agents into production is, how do I get access to those tools first? How do I make sure that they're good tools? And second, how do I make sure that just like I use an app and I have to log into that app and then that app knows who I am, how do I build that same thing with AI agents? So those 3 pieces are going to be very important. But start first very easily with, and all an agent is a prompt and access to tools. And you can do that today by connecting any MCP client that you've got, like Cursor or ChatGPT or Claude Code, directly to an MCP client, any MCP server, and saying, "Hey, do this specific task for me," and you're on your way already to building an AI agent.